then the spacing between consecutive momentum values, which goes like 1 over the length, becomes so small that you can basically approximate this dispersion as a continuous function called the band structure. This band structure is basically a visual representation of what the allowed quantum states are as a function of momentum. Now, this band structure may or may not have a gap at some point, but if it does, then this turns out to have important ramifications on the transport properties of the material. To understand why, let me first define something called the Fermi level, as the energy at which the highest energy electron exists. You can think of gradually filling up the band structure with electrons. The last electron to enter the band structure lies at the Fermi level. Now, let's place our Fermi level inside the gap, and let's think about perturbing this system with some characteristic energy scale. If the magnitude of the gap is much larger than this characteristic energy scale, then there's a sense in which the electrons simply won't respond to the perturbation, because it's not giving them enough energy to jump the gap and reach the next available quantum energy state. This results in electrically insulating behavior in the special case of the perturbation corresponding to an applied voltage bias, and the response being the motion of the electrons. Now, the opposite end of this extreme is, of course, the gapless case, which would result in electrically conducting behavior by virtue of the fact that for all values of the Fermi level, there's always an infinitesimally close quantum energy state for the electrons to respond with. Okay, but let's focus for the moment on the insulators. That is, after all, the purpose of the talk. And let's think about things topologically. This amounts to asking what are the topological equivalency classes